Founding fathers developed a lot of different methods. We'll review them, but Alexander Hamilton has suggested the most convenient and easy to use and easier to understand method. And this method, so-called Hamilton apportionment method, was used for more than a century or about a century. It is kind of simple and convenient, but it has several flaws that we will also discuss here, and that's why it's not used anymore for legislature. In 1881, the Alabama paradox was first discovered. Under Hamilton's method, Alabama would receive fewer representatives in a larger house. So in 1881, they decided to increase the Congress from 299 to 300 members. And when they used the Hamilton method to reapportion representative, everybody was surprised that Alabama lost a representative. According to new apportionment, Alabama got only seven representatives. You will see why it happens, and it usually happens with smaller states. So the possibility that the addition of a legislative seat will cause a state to lose a seat is called Alabama paradox. In 1890, it happened again with Arkansas. They increased the House from 359 to 360 by one member, and Arkansas lost their representatives. So how to find a method to avoid Alabama paradox? There are also other paradoxes, and in this section we only talk about Hamilton method. And since it's not used for legislature, we'll use it for example, with the consortium board. So suppose that the company has 3 departments with 4,700 stockholders, 3,700 stockholders, and 1,600 stockholders. The total is 10,000. First, we determine the percent of stockholders for every department. So it means we take 4,700 and divide by the total, 10,000. So 47% or 0.47. To determine the exact number of board members, we multiply this percentage, 47, by the number of representatives. So we assign 9 seats in the consortium board. So we take the percentage, 0.47, and multiply by 9. We get the exact number of board members deserved. You see, it's a fractional number. And now we first assign the integer part. So step 1. Step 1, we assign the integer part 4, 3, and 1. We find the total. The sum equals to 8. It means we have 1 extra. We assign 9 seats, so we have one extra representative. And now we look at the decimal parts. So on step 2, we look at the decimal parts. What is the largest? We have 23, 33, and 44. 44 is the largest decimal part. So we give this extra to the company C. C gets an extra representative, plus 1. Sometimes there are 2 or 3 extras. The rule is that there must be less extras than the number of companies or of groups that we consider. So here we have 3 companies, so the number of extras can be either 1 or 2. It cannot be 0, it cannot be 3. So then the final apportionment is 4A gets 4, B gets 3, C gets 2 representatives. On these slides, you see all these steps written down. So first, find the percent of stockholders. So we find the total population. So 55 plus 65 plus 80, 200. And then we find, for each group, we find the percentage, 55 over 20, 65, over 200, over 280 over 200. And then we multiply this fraction by the size of the board. So we have here 11. So multiply by 11, multiply by 11, multiply by 11. So 55 over 200 multiplied by 11 is 3025. Here you don't need so many digits. Digits. Actually, 2 digits are usually enough. 1 digit is not enough. So keep at least 2 digits after the point. So 3.5. Next step, we assign the integer part to every company. 3, 3, and 4. Now we determine how many extra seats do we have. 3 plus 3 plus 4 equals 10. So the sum equals 10. Therefore, we have 1 extra. And it goes to the company with the greatest fractional part. The fractional parts are 0 to 5, 5, 7, 5, and you see that the greatest fractional part is 0.575. So we get an extra representative to the company B, and the final apportionment is 3, 4, and 4. That's all, very easy method. Let us do it another couple of times. So the board, suppose that we want to increase the size of the board to 10 members. So the number of board members deserved will be 0.47 times 10, 4.7, 0.37 times 10, 3.7, and 0.16, 16% times 10, the number of representatives to assign will be 1.6. When we multiply by 10, we move decimal point 1 place to the right. Okay, now we assign the integer parts 4, 3, and 1. Then we look on the fractional parts. Oh, we have 2 equal 7 and 7, but happily we have 2 extras to assign. So the sum this time is 8. So we have 2 extras to assign, and we give them to A and B, both having the fractional part 7. So the final apportionment is 5, 4, and 1. And here we see the Alabama paradox occur. You see that, maybe remember that company C got 2 seats when they're assigned 9 members, and now C gets only 1 seat. So the problem, it happens because we reassign representatives every time we make our calculation. We forget what was assigned previously and started from the beginning again and again. It causes paradoxes, which one of them is the Alabama paradox. Another topic that will also be on the test, measuring fairness or unfairness of the apportionment. And first we introduce the average constituency, the constituency of a state. It is the fraction or the quotient, the population of the state divided by the number of representatives from the state. Like Texas has 29.4 millions. Now Texas has 38 representatives. So this fraction gives the average constituency of Texas. And this fraction shows how many people, constituents, are represented by one person. One of the 38 representatives represents this number of constituents. The greater average constituency, the more poorly represented is the state. The representatives are elected to a 2-year term serving the people of a specific congressional district. The number of voting representatives in the House is fixed by law at no more than 435. The ratio for the whole country is 759,000. We can find the constituency for every kind of groups. For example, for electrician union that has 420 members, and plumbers union with 440 members and 4 representatives. So for electricians, we divide the population by the number of representatives and get the average constituency 140. For plumbers, we take the population 440 and divide by the number of representatives and get the average constituency 110. So each of 4 representatives represent 110 plumbers. And you see that 140 is greater than 110, so electricians are more poorly represented. Absolute unfairness is just the difference between 2 constituencies. So it must be positive. That's why we subtract the average constituencies of one state minus greatest average constituency minus smallest average constituency. Let us consider Viewers Guild and Artist Alliance. We are given the population and the number of delegates, 6 and 5. First we find the average constituency, population divided by the number of delegates for Viewers Guild, for Artist Alliance. So we see that Artist Alliance is more poorly represented. Poorly represented. So, and the absolute unfairness is 289 minus 257 is 32. So it tells us something, but actually to compare different unfairnesses, we need a relative number. That's why we have also a relative unfairness. So returning to one of the previous examples with Viewers Guild and Artist Alliance, they have average constituencies 257 and 289. The absolute unfairness is the difference between them, 289 minus 257. And the absolute unfairness, we must divide 32 by the smaller constituency is 257, so we divide 32 by 257 and get a relative unfairness. Relative unfairness can be a very small number, much less than than 1. And so when you do the homework, look what is written in the problem. It often asks you to round to 4 digits after the point. Sometimes 3, but more often to 4. Okay. the same. The average constituency of Alaska is 709, of Florida 795. The difference is 86, and the relative unfairness we divide by the smaller one. The second method that we study in the course is the Huntington-Hill method. But first, we also discuss the apportionment criterion. I do not ask for apportionment criterion on the test because it's very complicated, but you have at least one homework with this method so that it helps to understand how the Huntington-Hill method works, but it involves much more work. So important thing that you know how to Huntington-Hill method works. It's the method how the U.S. Congress is assigned right now. But you also have the apportionment criterion in this course. So what is it about? When assigning a representative among several parties, make the assignment so that it gives the smallest relative unfairness. Suppose that we have state A and state B, and they have the current number of representatives. Currently, state A has 4 representatives, and state B has 6 representatives. It is fixed. We do not reapportion all representatives as Hamilton method does. We fix these 4 and 6 representatives, and the question is, if we increase the representative body, who will get the next representative, this extra representative? Who deserves this additional one? And we decide what to choose. Either to give this one to the state A or to state B. Either A gets 1 and B has 6, or state A keeps 4 representatives and state B gets an extra. We consider both situation, find relative unfairness, and here also find relative unfairness, and we look in which case, in case A or case B, the unfairness is smaller, is less. So you see, it will take some time. So assume that state A has a population of 13,680 and 5 representatives. State B has population 6,180 and 2 representatives. Use the apportionment criterion to determine which state is more deserving of an additional representative. Okay, stage 1. Assume that we give an additional representative to A instead of B. So A will have 6 representatives and B will have the same 2. Okay, we find the average constituency, A's average constituency, B's average constituency. So A's constituency is small, it means that B is now more poorly represented. It's of course because A got an extra representative. And we find the relative unfairness, which is 0.355. Let us summarize this in the table. So original population, it doesn't change. So the extra representative goes to A, and the relative unfairness is 0.355. Okay, on stage 2, we give this extra representative to the state B. And we do the same. We find average constituency, the new average constituencies for A and for B. Of course, now A is more poorly represented, so on stage A, B is more poorly represented. And we find the relative unfairness. We subtract the constituencies and divide by the smaller one, by 2060. And now we get the second, the relative unfairness, 0.328, and this relative unfairness on stage 2 is smaller than the relative unfairness on the stage 1. It means it will be less unfair to assign this representative to B. So this is how this method works. Smaller relative unfairness happens when we assign the representative to B. So we assign this representative to B. Okay. So this is again the same table. The state B gets an extra representative, and we can compare the method, the apportionment criterion method, with Hamilton method. Remember, by Hamilton, first we find the fraction of the population, so the population of A divided by the total population, and multiply by the total number of representatives. So we have 2 plus 5 plus 1, 8 representatives to apportion. So that's why we multiply this fraction by 8, 5.511. The same for B, population of B divided by the total population. This is total. By total population and multiply by 8, 2.489. Okay, first we assign 5 and 2, the integer parts, and then we assign the next straight representative to the state with greatest fractional part, 5 and 4. 5 is greater than 4, so A gets an extra representative and gets 6 representatives. You see, different methods may give different apportionment. From the mathematical point of view, Huntington-Hill method, so-called apportionment principle, generalize the apportionment criterion. That's why we study apportionment criterion. It's like giving the geometrical average for constituencies, but we don't care about mathematical part of this. It is important for us that we know how to use this method. So Huntington and Hill were two mathematicians. At the beginning of 20th century, they spent a big group of mathematicians spent a lot of time, several years, to develop the method, the most fair method and simple, because you cannot use apportionment criterion for 50-something states. It's too complicated. They have developed this method, but still, it developed in 1920, 1921, something, but still it wasn't used. And even the Congress was not assigned because the congressman could not decide which method to use to assign representative. And only shortly before the World War II, the Huntington-Hill method was finally used to be the method to assign the US Congress. Okay, returning to the mathematics. In Huntington-Hill apportionment principle, we use so-called Huntington-Hill numbers for every state. So the Huntington-Hill number is the population squared divided by the number of representatives assigned to the moment, the present number of representatives. So already been allotted X and Y. Yes, so the present number of representatives and divided by X plus 1. So divided by X and divided by X plus 1. We calculate these numbers for both states, state X, state Y, and then we'll look which Huntington-Hill number is greater. The greater Huntington-Hill number, the more deserving the representative. And you see that it is a little bit similar to constituencies, but they have population squared, and in the denominator we have X and X plus 1. So the logic is the same. So the greater the number, like the greater the constituency, the greater the HH number, the more poorly represented, the more deserving a new representative. Okay? So let us apply the method to not to the states, but the nurse community at General Hospital. Suppose that there are 330 full-time nurses and 148 part-time nurses, and we know the present representation for the nursing supervisor has chosen 4 full-time nurses and 2 part-time nurses to serve in a committee to evaluate proposed nursing guidelines. Decide whether the 7th nurse, so we increase the representative body, and we decide which group will get this extra, the 7 nurses. So we will compare the Huntington-Hill numbers for the 2 groups. First group, full-time nurses. Square the population divided by the present number of representatives and divided by present plus 5, 4 plus 5. So if you use your in-hand calculator, so there is a possibility to make a mistake, so you take 300, 220, you square this, then you divide by 4, and then you multiply by 5. It's not correct, because if you type divide by 4, multiply by 5, it will multiply the fraction by 5, the whole fraction. You need this 5 in the denominator, so either you put 4 times 5 in the parentheses, it's good, or you type 320, then you square it, and then you divide by 4, divide by 5, but without parentheses. It will also work. If you use an online calculator like Desmos, then you will see what you are doing. You will see that you type 4 times 5 in the denominator. Okay, the second group, part-time nurses. Population squared divided by the present representation and divided by present representation plus 1, divided by 2 and by 3. Okay, 2 Huntington-Hill numbers, 5,000 and 3,000. You see clearly, much better than by Hamilton method. You see what number is greater. 5,000 is greater than 3,000. Therefore, full-time nurses deserve next representative, 7th representative. Okay, we can apply the method to the consortium board. So we sometimes sometimes the problem gives you the present representation, and the question is who deserves the next representative or who gets the next representative. Sometimes we construct the table, we start from the beginning. We first assign one seat to each company, and then we calculate the Huntington Hill numbers for every next representative. So the first we assign one representative to each A, B, and C. So the current or the present number of representatives is 1 for everybody. The 1 plus 1, the next number of representatives will be 2. So the denominators are the same for every company. So in Huntington Hill numbers, you will see such tables. The first table suggests that every group has one representative, and when we assign the second one. So we find the Huntington Hill numbers, and we decide who gets the second one. Okay, we have 1,104, we have 600, and we have 100. Okay, 1,000 is definitely greater. So the second representative goes to A. So first they all have one representative, and now A gets the second one. And we cross out this Huntington Hill number from the table, and we go to the next. For A, we go to the next line in the table. So for A, the present number will be 2. So the Huntington Hill number will be calculated like this: 47 squared divided by 2 times 3. Okay, here we have this table. So first we assign one representative to everybody. Then we look at the Huntington Hill numbers. The greatest is here. A gets the second one. And for A, we consider the second line of the table, 47 squared divided by 2 times 3. And now we compare those Huntington Hill numbers. 300, 600, 128. Now you see that the greatest is the Huntington Hill number for B. So B gets the next representative. How many have we already assigned? 2, 2, and 1, 5. But we are assigning 8. We have 3 more to assign. We need next HH numbers in the table. Let us move on here. So we have, on this step, we have 2 for A, 2 for B, 1 for B. This number have been used. This number have been used. Now we're searching for the greatest Huntington Hill number from the remaining in the table. They're usually on the top, and now we have 368, the greatest number. We cross it off, and we give the next representative to A. Now we have 6. And again, we look for the greatest Huntington Hill number. Now we have 184, 200. 200 is the greatest one. So we cross off this, and oops. And the next representative goes to B. So that was the 6th, the 7th, and we have 1 more to assign. Let us see what numbers we have. 184, 114, 128, 184 is the greatest from those left, and so the 8th representative goes to A. And as a result, we have assigned 4 representatives to A, 2 to B, and 1 to C. So this is how the Huntington Hill method works. On the test and on the quiz, I will ask you to fill out the table not the whole table, it will be partially filled. So you will have to find a couple of cells. For example, suppose that there is no number in the third line. So how do you calculate them? You take the population, 37 squared. So we, to make the numbers convenient, in this example, we use population in hundreds. You will see in the problem what numbers to use. Okay, in hundreds, and we divide by the present number, 3, or current number, and by 3 plus 1, by 4. For C, 6 population squared divided by present number, 3, and divided by 4. So you find missing HH numbers, and then you assign the representative. So the first three are always assigned. So because first we assign one rep to every company. We start assigning from the 4th place. And the 4th goes to the largest HH number, then the second largest, and so on and so on. And when we have the problems with Huntington Hill numbers, I usually ask you to show the order of the in which you assign the representatives. And this is the order, decreasing order of Huntington Hill numbers. Okay, let us do one more example. Suppose that we assign police officers, 7 police officers in a small town. The town is divided into 3 regions. The police chief has gathered data regarding to the number of incidents that have occurred in each region. So region 1, 107, region 2, 65 incidents, region 3, 43 incidents. So instead of populations, here we have number of incidents, and the number of seats is the number of police officers to assign. So so we don't want the region lose a police officer. That's why we don't use a Hamilton method here. We use a Huntington Hill method. Because Hamilton method reassigns every time when we increase the representative borders, but it may happen that the town gets an extra police officer, and one of the region would lose representation, and that's why we use Huntington Hill, more complicated, but more fair Huntington Hill method. So we start in this example, just to show the difference. In the left, in the first column, you see not the current number of representative, but the future number of representative. So if the current number is 1, 2, 3, and 4. So on the usually we use the current number of representative, but in this example it gives you the future number. If given the next officer, the number region would have will be 2, 3, or 4. Okay, first we need to find Huntington Hill numbers. The number of incidents squared, 107 squared, divided by current representation, 1, and divided by representation when given the next officer. So 5,724.5. For in the next line, the population is the same. In every column, we have the same numerator, 107, divided by current number of officers, future number of officers, 1,908.2. The next, so if the current is 3, so the numerator is the same, the number of crimes for this period of time that we consider, divided by current, by future. Okay, 954.1. And the last line, 107 squared divided by 4 times 5, 572.5. And the same for the second column, the numerator will be different. So 65 squared divided by present representation, future representation, 2112.5, and so on. And here 43 squared divided by 1 by 2, 904.5, 308.2, 154.1, 704.2, 352.1. Okay, the problem usually tells you how to round the numbers. Okay, now let us decide how we will assign the officers. And first, every region gets 1 officer. Starting point, every state must have at least one congressman, and we apply the Hunting Hill method after that. Okay, now look what region has the greatest Hunting Hill number, and answer the poll question. Who gets the 4th representative? Region 1, Region 2, or Region 3? What region will get the 4th representative? You must look at the Hunting Hill numbers. The greater the number, so the region with the greatest number, HH number, must get the representative. So we have 5,700, 2,100, and 900. So who gets the next representative? I'm rather surprised with the results. Are you answering randomly? Wait a minute, you are making it worse. Okay, so the 3 representatives are already assigned. The question is who gets the 4th representative? And we choose the region with the greatest HH number. Where is the greatest HH number in the table? So that is the question. Okay. Okay. I don't know. I don't understand why it is so difficult. Maybe you will help me to understand this. Let us see at the table. Let's look at the table. We have 5724, 2112, 924. 5,000, 2,000, and less than 1,000. 5,000 is definitely greater than the other 2 numbers. It means the 4th representative goes to region 1. And we cross out the number from the table. Now we look at the other numbers. We have 1,900, 2,100, and 900. Now the second region has the greatest HH number, the greatest HH number. 2000 is greater than 1000. So the fifth representative goes to the region 2. And we cross off the HH number that we have used. Now, let us look what we have now. We have 1900, 700, and 900. Of course, now that region 1 has the greatest HH number, so the sixth representative goes to the region 1. Let me change the color here. So this is we have used for the 5th. Okay. Now let us compare the numbers. We have 954, 704, and 927. 954 is greater. We use this number and we send the 7th officer to the region 1. So in this case, if there will be an 8th officer, then we look at the numbers that are left in the table, and the greatest number will be 924 for region 3. So the eighth officer will be assigned to the region 3. Okay, so if it would be the 9th, then we look at the numbers that are left in the table. The greatest in each column are 500, 700, and 300. Then the 9th officer will be assigned to the region 2, and so on. If we will use the last number in the line, in the 4th line, 572, we'll possibly use it at the 10th officer. Then we will need to add another line to this table, and so on. Okay. So this Huntington Hill method, for some reason, as always, is difficult, but I really don't see where could be the difficulty here. So the Huntington Hill apportionment principle was developed by mathematicians Edward Huntington and Joseph Hill, and signed into law only. So developed in 1920 something, but was signed into law only in 1941. Although this method avoids the Alabama paradox, it's still not perfect. We have two criteria to evaluate the fairness. First, the method should not be subject of the Alabama or other similar paradoxes. We will discuss them later. And second, the apportionment should satisfy the quarter rule. And this is the problem with the Huntington Hill method. The quarter rule tells that no state should be apportioned the number of seeds that are different from the exact quarter by more than 1. So the exact quarter, remember, in Hamilton method. In Hamilton method, we have found the exact quarter. It was a number with a fractional part. We cannot assign a fractional part of a representative. And with Huntington Hill method, it may happen that the number assigned is too far from the exact quarter. So if the exact number is 31.46, for example, then the number apportioned must be either 31 or 32. So this number 31.46 is between the integer numbers 31 and 32. The state cannot receive 30 or 33 representatives. But by Hunting-Hill method, it can happen that the state receives a number that doesn't satisfy the quarter rule. So you can search on internet about the impossibility theorems. There are different formulations for that, but the main idea is that it is impossible to find the apportionment method that avoids the paradoxes and at the same time satisfies the quarter rule. It's always a political decision which method to use and how to use this method. Okay. Okay. So since we have another 10 minutes, let us return to the previous section. If you don't have questions, of course. Let us return to section 10.1. So you remember that you have a test next week. The test will cover chapter 8 and chapter 10. I plan to open the review assignment later today, and maybe make a short review. So we will finish chapter 10 on the next lecture on Thursday and make a short review. And wait a minute. I need the whole screen this time. Let me know if it would not work. So because I want to use the whole screen. Okay, suppose that we want to assign 30 teaching assistants to 3 different courses: college algebra, contemporary math, and trigonometry. And we will use a Hamilton method. Let me change the color here. Hamilton method. Okay, recall, in Hamilton method, we first find the sum. First find the sum. 755 plus 430 plus 165. The total population is 1350. Then we find the proportional part of each group for each group. So 755 divided by 1350, 430 divided by 1350, and 165 divided by 1350. And you can write this proportion, this fraction, but you can directly multiply by the number of representatives to assign. We assign 30 teaching assistants. So let us find this. So first, college algebra, 755 students divided by the total, the answer from the previous step, and multiplied by 30. So so what we have found on this step is exact quarter. And it is 16.78 for contemporary math, 430. The number is 956. We usually don't need more than 2 decimal places, and the last one 165 for trigonometry, and the exact quarter is 3.67. Okay, we first assign the integer part. Integer part 16, 9, and 3. 16 plus 9 plus 3, 28. So we have two extras. Now we'll look at the fractional parts, 78, 56, 67. The largest fractional part is 78, so we get one extra to college algebra. And the second largest is 67, so the second extra goes to trigonometry, plus 1. So the assignment is 17, 9, and 4. Let us use the Huntington-Hill method, since we have time. Okay, it does not work for some reason. Okay, cannot copy the slide. Okay, Huntington-Hill method. We need Huntington-Hill numbers. So 755 squared. We start from the first line in the table. Current number of representatives is 1. The future number of representatives is 2. So 755 squared divided by 1 times 2. So the first Huntington-Hill number for college algebra is, let us write it in 1000. 285. So let us I will round to thousands. The rest, ignore the rest since the numbers are too big. In the next line, we will have 2 times 3. It will be 95,000. Oh no, it will, wait a minute, it will be too long. The 16 represent, let us do it shorter. Let us only decide about the last 2 representatives. Okay, suppose that college algebra has 16 representatives, contemporary math 9, and trigonometry 3. So the present number is 16, the next will be 17. We decide about the next. Suppose that this is the current apportionment, and the next will be 16 times 17. You see, 16 and 17 are both in the denominator, and the HH number will be 2096. And the next number will be 17 times 18. So the next number in the table will be 1863. Okay, returning to the second group, the population 430. 430 squared. The present representation is 9. The future representation 10. 9 plus 1 is 10. So the HH number will be 2054. And the last one, 165 squared divided by the present representation is 3, the current number of TAs, multiplied by the future, by 4. And we get 2,269. Okay, according to HH method, the greatest Huntington Hill number is by trigonometry, so trigonometry gets +1. And to use this method, we actually need to know the next HH number, which is with the current 4, the future number 5. So it will be 4 times 5 in the denominator. So the next HH number, 1,361. So now let us look at the number, compare the numbers 2096 to 2054 and 1361. Now the greatest number is of College algebra, so it gets the next representation. So in this example, we got the same assignment by Huntington-Hill method and by Hamilton method. Okay, so still have 2 more minutes. So do you have any questions? So if you don't, then thank you and have a good day. Thank you. I am glad to hear it. Okay. Yes, the question will definitely say for the homework for 10.1 will ask for Hamilton method, the homework for 10.2 will ask for Huntington-Hill method. And on the test, there will be 2 different problems, and they will say for Huntington-Hill method, you will see a table of Huntington-Hill numbers. I just use the same method for the 2 different methods for the same problem, just to compare them. Okay, you're welcome.